Section 14.2, Reaction Rates. The speed of an event is defined as the change that occurs in any given interval of time. Whenever we talk about speed, we necessarily bring the notion of time. For example, the speed of a car is expressed as the change in the car's position over a certain period of time. The units of this speed are usually miles per hour. That is, the quantity of that's changing, the position, measured in miles, divided by the time interval in hours. Similarly, the speed of a chemical reaction is its reaction rate, is the change in the concentration of the reactants or the products per unit of time. Thus, the units for reaction rates are usually molarity per second. That is, the change in the concentration, measured in molarity, divided by a time interval in seconds. Let's consider a simple hypothetical reaction, A going to B, depicted in figure 14.3. Each red sphere represents 1/100th of a mole of concentration A. Each blue sphere represents 1/100th of a mole of material B, and the container has a volume of 1 liter. At the beginning of the reaction, there's 1 mole of A, so the concentration is 1 mole per liter, or 1 molar concentration. After 20 seconds, the concentration has fallen to 0.54 molar, whereas the concentration of B has risen to 0.46 molar. The sum of the concentration is still 1 molar, because 1 mole of B is produced for each mole of A that reacts. After 40 seconds, the concentration of A is 0.3 molar, and that of B is 0.7 molar. The rate of this reaction can be expressed either as the rate of the disappearance of reactant A or as the rate of appearance of product B. The average rate of appearance of B over a particular time interval is given by the change in concentration of B divided in the change of time. So the average rate of appearance of B is the change in the concentration of B over the change in time. That equals the concentration at the second time, T2, minus the concentration at the first time, T1, divided by the change in time. We use brackets around the chemical formula, as in bracket B, to indicate the concentration of the substance in molarity. The Greek letter delta is read change in and is always equal to the final quantity minus the initial quantity. The average rate of appearance of B over the 20-second interval from the beginning of the reaction, T1 equals 0 to T2 equals 20, is given by the average rate of B was 0.46 molar minus 0 molar over the 20-second minus 0 second. That gives you a concentration of, or a rate of, 2.3 times 10 to the negative 2 molarity per second. We could equally well express the rate of reaction with respect to the changing concentration of the reactant A. In this case, we would be describing the rate of disappearance of A, which we could express as the average rate of disappearance of A is negative, because it's disappearing, change in the concentration of A divided by the change in time. Notice that the minus sign is in this equation. By convention, rates are always expressed as positive quantities. Because A is decreasing with time, the delta A is a negative number. We use the negative sign to convert the negative delta A to the positive rate. Because 1 molecule of A is consumed for every molecule of B that forms, the average rate of disappearance of A equals the average rate of appearance of B, as calculation shows. Average rate equals negative change in concentration of A per change in time equals minus 0.54 molar minus 1 molar over 20 minus 0 seconds equals 2.3 times 10 to the negative 2 molarity per second. Change of rate with time. Now let's consider an actual chemical reaction, one that occurs when butyl chloride is placed in water. The products formed are butyl alcohol and hydrochloric acid. Suppose that we prepare a zero point 0.1 molar aqueous solution of the butyl chloride and then measure the concentration of the butyl chloride at various times after zero. The time of reactants are mixed, thereby indicating the reaction. The resultant data are shown in the first two columns of Table 14.1. We can use the data to calculate the average rate of disappearance of butyl chloride over the intervals between measurements. These rates are given in the third column. Notice that the average rate decreases over the 50-second interval for the first several measurements and continues to decrease over even larger intervals through the remaining measurements. It's typical for the rates to decrease as the reaction proceeds because the concentration of reactants decreases. The change in the rate of reaction proceeds as is seen in the graph in the concentration of butyl chloride versus time. Notice how the steepness of the curve decreases with time, indicating a decreased rate of reaction. Instantaneous rate. Graphs showing how the concentration of a reactant or a product changes with time, such as the graph in Figure 14.4, allow us to evaluate the instantaneous rate, the rate at a particular moment in the reaction. The instantaneous rate is derived from the slope or the tangent of the curve at the point of interest. We have drawn two tangents in Figure 14.4, one at t equals 0 and the other at t equals 600 seconds. The slopes of these tangents give the instantaneous rates at these times. For example, to determine the instantaneous rate at 600 seconds, we draw the tangent to the curve at this time, then construct the horizontal and vertical lines to form the right triangle as shown. The slope of the ratio of the height of the vertical side to the length of the horizontal side is the instantaneous rate. So the instantaneous rate is the negative change in butyl chloride over time, which is negative 0.017 minus 0.042 molar over 800 minus 400 seconds, which is a rate of 6.3 times 10 to the negative 5 molarity per second. In discussions that follow, the term rate means instantaneous rate unless indicated otherwise. The instantaneous rate at t equals 0 is called the initial rate of the reaction. To understand better the difference between the average rate and the instantaneous rate, imagine that you've just driven 98 miles in 2 hours. Your average speed is 49 miles per hour, whereas your instantaneous speed at any moment is the speedometer reading at that time. Reaction rates and stoichiometry. During our earlier discussion of the hypothetical reaction A goes to B, we saw that the stoichiometry requires the rate of disappearance of A equals the rate of appearance of B. Likewise, the stoichiometry of equation 14.3 indicates that 1 mole of butyl alcohol is produced for each mole of butyl chloride consumed. Therefore, the rate of appearance of butyl alcohol equals the rate of disappearance of butyl chloride. The rate is negative change in butyl chloride over time equals the change of butyl alcohol over time. What happens when the stoichiometric relationship is not 1-to-1? For example, consider this reaction. 2 moles of hydrogen iodide break apart to form 1 mole of hydrogen gas plus 1 mole of iodine. We can measure the rate of disappearance of hydroiodide or the rate of appearance of either hydrogen gas or iodine. Because 2 moles of hydroiodide disappear for each mole of hydrogen or iodine that forms, the rate of disappearance of hydroiodide is twice the rate of appearance of either H2 or I2. To equate the rates, we must therefore divide the rate of disappearance of I2 by 2, its coefficient in the balanced chemical equation. In general, for this reaction, little a times big A plus little b big B goes to little b c times big C plus little d times big D. The rate is given by negative 1 over the moles of A times the change in concentration of A per time equals negative 1 over the moles of B times the change in concentration of B per time equals positive 1 over the moles of C times the rate of change of concentration of C per time equals positive 1 over the moles of D times the change of concentration of D per time. When we speak of the rate of reaction without specifying a particular reactant or a product, we will mean it in this sense.